Good afternoon, everyone. I'm Nancy Molenda, VP of Communications for the Aluminum Extruders Council. Our webinar, Designing Aluminum Welds, is presented by Randy Kissell. Before we get started, I have some housekeeping announcements. All computer audio and telephone lines are muted, so if you have a question during the webinar, please select Questions or Chat from the toolbar. Type your question in the dialog box and our presenter will address your question at the end of the presentation. For those of you who are not familiar with us, the Aluminum Extruders Council is a trade association dedicated to providing information and education about aluminum extrusion and its processes. We help manufacturers, engineers, architects, and others discover why aluminum extrusion is the preferred material process for more effective products. AEC is also focused on enhancing the ability of its members to meet evolving market demands through knowledge sharing and best practices. For more information, visit our website at aec.org. Now, let me introduce today's speaker. Randy Kissell has more than 40 years of experience designing aluminum structures, and he co-holds numerous U.S. patents on aluminum structures. He co-authored Aluminum Structures, a guide to their specifications and design, published by John Wiley. Randy served as secretary of the Aluminum Association's Engineering Advisory Committee, responsible for the specification for aluminum structures, and chaired the American Welding Society's Subcommittee on Aluminum Structures. He also conducted ASCE's Designing Aluminum Structures seminar from 2002 through 2020, as well as similar seminars for the National Council of Structural Engineering Associations and the American Welding Society. In his presentation today, Randy will be describing aluminum welding processes, the codes that govern their use and design, and methods for determining the strength of aluminum welds. Welcome, Randy.
Thanks, Nancy. I appreciate the introduction. You said some nice things about me, but I shouldn't be too surprised because I told you to say that. But I wanted to just by way of introduction, let you all know that my contact information is available here. Feel free to give me a call. I actually recently retired a couple of weeks ago. So I still have my business email address, Trinity Consultants, but you can reach me either at that address or my Gmail address here. And I'm always happy to answer questions. Now that I've retired, it might take me a moment or two to immediately get back to you, but I'm happy to do so. I want to sort of start out here by showing you, reminding myself by showing you this very nice looking aluminum weld, which has me recalling a story. Early in my career, in the 1980s, I was working down in Texas during the oil boom. And there must have been a labor shortage because even though I was relatively young, I rose to be the engineering manager at an aluminum fabricator company in the Houston area. And as engineering manager, I was responsible for hiring and firing drafters, engineers, and cost estimators. And frankly, I didn't know a whole lot about that part of the business. And human resources was not something that had been invented yet. We just had employees and we were lucky to have them. So I decided that in recruiting and interviewing potential hires, I needed to get up to speed. And so I read some article in some magazines suggesting that the way to get to know a person was to ask them questions, get them talking about themselves. And a good question to ask was, what are your biggest weaknesses and what are your biggest strengths? So the first guy that I'm about to interview comes in and I'm sort of fumbling around for what to say. And then I realized, oh yeah, I've got to ask him a question. So I said to him, so what's your biggest weakness? And without hesitating, the guy said, oh, my honesty. And I was immediately taken aback because I was surprised. And I said, well, I don't think of honesty as a weakness. And he said, yeah, like I care what you think. Now, I mentioned that story because I want to be honest with you all. I am not an aluminum welder. I never have been, couldn't weld, make this weld worth a darn and wouldn't even try. But I know lot about aluminum welding from administrative and engineering and design aspects. And I know a lot of good aluminum welders, and people are familiar with the actual fabrication processes that I can plug you in with should you need that. But just wanted to get that out above and be totally above board with you all. Now, what we'll talk about here today are basically three aspects of aluminum welding, or three issues that we'll tackle today, just as an introduction to the topic. I'll give a general introduction to the lay of the land when it comes to aluminum welding, what processes are used, and what sort of design codes affect those. Then we'll talk a little bit about metallurgy, the metallurgy of the base metals, that is the parts that are to be joined together by welding. And then the filler metals, that is the metal that's used, molten metal that's deposited in the joint to actually fuse the base metals together. And then finally, we'll talk a little bit about design, how you come up with the strength or nominal design strengths with safety factors and so forth for various types of aluminum welds, particularly groove welds and fillet welds. And by way of introduction here, we're going to look at some examples of welded aluminum structures. Examples or go-bys are I think, a very good starting point for anyone. It's always good to see what works and what doesn't work. And if you're going to do something that's different from what's traditionally been welded in aluminum, is not a good example, you might want to say that you need to think twice about that. Not to say it's impossible, but you might want to have the caution flags go up and be a little more careful. We'll talk a little bit about various aluminum joining methods because, and I'll be the first one to say this to people in general, sometimes the best aluminum weld you make is the one you don't make. In other words, sometimes welding is not the way to join aluminum. There are other ways that are more suitable for given applications. We'll talk a little bit about that. I'll also talk about sources of information. We're only going to have an hour here today, and even if I just talk nonstop for an hour about information that you could use on aluminum welding, I could never cover it all. There's a lot more, and I'll point you in the direction of some additional information that may be helpful. And we're going to talk about the Bible of aluminum welding when it comes to the United States anyway, and that's the American Welding Society's Structural Welding Code for Aluminum, otherwise known as D as in Delta 1.2. And if you're just interested a little bit more in aluminum in general, I recently did a video for a college, and it's a YouTube video. If you search for The End of Heavy Metal, How Aluminum Saved Civilization, you can see the video. I don't know, it's about 45, 50 minutes. Puts aluminum in its general context, and you might find that interesting. Includes issues like aluminum welding and a little bit larger issues. So just if you want to have some fun, you're welcome to see that. Now, when it comes to examples of welded aluminum structures, there have been very many different types of applications that are welded in aluminum and have been very successful. And I don't want to turn you off from aluminum welding, but I do want to say that there are a lot of cautionary notes, and we'll cover those. But things like guardrails and handrails are very frequently welded in aluminum, and they typically use hollow shapes like pipes or tubes, but not necessarily. And the weld at the base of the post of most guardrails is a very critical area because that's where the stresses are the highest due to lateral loads on the guardrails or handrails. And so that can be an area that particularly comes up over and over again that I've noticed in my career. Any sort of tank or vessel, whether it be for pressure or low pressure applications, whether it be in a corrosive or a cryogenic or low temperature application where aluminum shines, if it's made from a part that's more than one plate or one extrusion, then it's going to involve welding typically because you need a liquid or airtight container. If various highway products such as overhead sign structures, road sign structures, the little panels that are used to handle signal devices and control traffic lights, light poles, otherwise known as luminaires in the highway business, many of those are made of welded aluminum. And that's a very good example of welding and post-weld heat treatment and many other features of welding aluminum. Highway trailers, whether they be horse trailers or trailers hauled by tractor trailers going down the road with various consumer goods in them, very often welded aluminum. And that's because they need to be lightweight. Pedestrian bridges like the one you see in this picture here, if they're in remote locations and need to be brought in off-road, typically want to use aluminum because it's light and very often they're welded. Here's an example of a floating roof. This is a roof that's placed inside of a large gasoline storage tank. As a matter of fact, this is for the infamous Colonial Pipeline, who recently made the news. And you can see here that there are fillet welds being used, as well as some rusty steel bolts. And we don't use mechanical connections in parallel with welded connections in aluminum, because we cannot share the load between the two of them in a reliable fashion. But we often use those connections in series. In other words, you'd have a fillet weld, and then connecting the other end of the part might be a bolted connection. So just to illustrate that that is a possibility and is done. Several years ago, I was involved in a bridge deck for the rehabilitation of an old suspension bridge. This is the Corbin Bridge in south central Pennsylvania over the Juniata River, 320-foot span. So it was a very long suspension bridge span of the late 1800s. But it was originally made with the ability to carry horse-drawn wagons across, and it had wooden planks for the bridge deck. Now, when automobile traffic was introduced in the early 1900s, they provided a paved roadway or deck on the bridge, but that was much heavier than what the bridge was designed for. And with deterioration of the superstructure and foundations over the years, the load limit had been severely curtailed. But by changing the bridge deck from a paved steel combination deck to an aluminum deck, they were able to more than triple the capacity of the bridge. And you can see here in this picture from the underside that mechanical fasteners were used in parts of to connect the various panels together that were aluminum extrusions that had been welded together in large 9 or 10 foot wide panels in the shop. So heads up there, we typically don't do aluminum welding in the field, but rather in the shop. Now, there's a lot of ways to connect things, and there's a lot of ways that mechanical engineers and structural engineers look at things, but my father-in-law always subscribed to the notion that we engineers made things way too complicated, and that really there's just one of two answers for every problem. That was WD-40 or duct tape. But if you don't subscribe to that theory, if you think that maybe life is a little more complicated, you're probably right. And then you might want to look at the larger view of various joining methods. And when it comes to joining methods, I think of mechanical fastened joints, welded joints, and adhesive bonded joints. And it's really worthwhile thinking about all of these and deciding which of these is the most appropriate for your particular application before you just assume that you need to weld something together. But when it comes to welding, there are different welding processes, and some of those could be categorized as fusion welding, and that'll be gas metal arc welding or gas tungsten arc welding, which we'll talk about in more depth. And then solid state welding, where we don't get above the melting point of the material. That's friction stir welding as a good example. We'll talk a little bit about that. And then there are processes which are done at temperatures below the melting point of aluminum, but above the melting point of the various filler metals that are used, the brazing and soldering materials. We won't talk about those because they're not typically used in structural applications, but they can be used to provide airtight or gas-tight sealed joints. Now, when it comes to the non-welding joining methods, mechanical fasteners, if they're used properly, not to share the loads with welds, but just as the entire connection, generally fall in one of four categories: bolts, rivets, screws, and pins. And you'll notice that next to each one of these on this slide, I've noted the aluminum design manual, part 1, and the particular section in that part that deals with that particular type of mechanical fastener. We'll talk a little bit more about the aluminum design manual here in a moment, but just keep in mind that there are different types of mechanical fasteners. They have different pros and cons, and sometimes they're a much better alternative to welding for reasons that we'll see. And I also want to mention adhesive connections because they are often used in structures. In fact, they're used in the aerospace industry for helicopter rotor blades as one example. And so they must be good for something. I mean, you trust your life to them essentially, but they're not addressed by building codes. And so they're not typically used in architectural applications. But I do want to mention that various types of caulks or sealants, such as silicone sealant or polysulfide sealants, can do an excellent job at non-structural joining of aluminum. For example, if you want to keep the weather out, or you want to join flashing together, or something designed for weather tightness, sealants can be a very good way to join aluminum together when you properly prepare the surfaces as the manufacturer directs. But coming back to welding, most people who do aluminum welding today are using an arc welding process, and there are two arc welding processes that are very popular. They're both inert gas shielded arc welding processes because an inert gas, and that is either argon or helium, is used to shield the arc and the base metal that goes molten from oxidation. Gas metal arc welding, sometimes referred to as MIG welding, metal inert gas, is one of the two processes, and gas tungsten arc welding, sometimes referred to as TIG welding, is the other. Now, these two have rather similar costs when it comes to the overall bottom line cost, but they have different applications, and gas metal arc welding is probably the more popular and the more commonly used today for reasons that we'll see. Now, there also is shielded metal arc welding, but it has some real problems when you try to use it in aluminum. There's a flux that's used to remove the oxide from the aluminum before welding, and that flux is very difficult to remove and causes problems down the road with corrosion, so it's not a recommended process. There are other aluminum welding processes. I already mentioned friction stir welding, and stud welding is another, either by arc welding or capacitor discharge processes, and plasma arc welding. Now, these are addressed by the American Welding Society Structural Welding Code D12, but there are yet even other welding processes that are perfectly good for aluminum, used, say, in the automotive industry: laser welding, resistance welding, electron beam welding, all sorts of exotic processes that have very narrow applications typically. We're not going to talk about those because they're not as widely used, and they tend to be for various niche applications. Well, coming back to gas metal arc welding, the way MIG welding is done is you have an electric arc that is inside the shield of inert gas, typically argon, but maybe a mixture of argon and helium. And the arc goes between the base metal and an electrode filler wire, which is being fed out of the tip of the gun you see in the lower right-hand corner here. Now, that electrode wire is being pulled off a spool, which is back in a cabinet, and this wire feed mechanism is going to deliver that wire to the arc through that gun, and it's going to be done at whatever speed you set the machine at. And therefore, this process is sometimes referred to as a semi-automatic process, since the machine is going to control the wire speed, and the operator or the welder is going to control the speed at which you move the gun along the joint. The other arc welding process, the TIG process, has also got an electric arc, but in this case, the arc is between the base metal and a non-consumable tungsten electrode, which is in a holder. So you see the holder here in the lower right. If I'm a right-handed welder, I'm holding that the gun, and I'm just basically striking that arc between the tip, that tungsten tip, and that tungsten is used because it's got a very high melting point, and the base metal. And if I want to add filler metal, I can do so with a rod held in my left hand that I feed into the joint. Now, if I don't use any filler metal, it's referred to as an autogenous weld, which is really just a fancy way of saying I'm melting the two parts together. And that's typically done with sheet metal. Now, TIG welding is much slower than MIG welding. A lot of people think the speed of welding is what's going to control your costs. That's not entirely true, but people like to weld quickly. They might tend to use MIG instead. And furthermore, TIG welding is typically best used on thin material, say a quarter of an inch thick or thinner. Now, before we leave the welding processes, though, we'll talk about friction stir welding. And friction stir welding is a relatively new process, patented in 1991 in the United Kingdom. And it's a really slick process. There's no edge prep in making a groove weld, so you don't have to bevel the sides of the joint or the parts. You don't use any filler metal. You don't use an electric arc. Therefore, you don't need any shielding gas, and therefore there are no fumes. And you can weld together alloys that can't be arc welded. And you do this all at a lower temperature than the melting temperature. In other words, instead of 1200 degrees, which is an average melting temperature for most aluminum alloys, you do it at 800 degrees, excuse me, and therefore you have less distortion and you have less heat effect affecting the base metal. So the process looks something like this. You have in the upper left-hand corner here, the tool, which is basically a rotating mechanism with a little thing. It looks like, it's called a pin, but it almost looks a little like a drill bit. That's plunged down into the joint between two budding parts, aluminum base metal parts. It's rotated, and once the heat, the heat of friction gets up to a certain point, then the rotating tool is traversed along the joint in the direction you see here from the upper left to the lower right, and then finally withdrawn from the part. Now, there can be an exit hole at the point of withdrawal, and therefore that can be an issue sometimes. Sometimes you need to use a runoff tab, as it's called, or you need to have the exit hole in a low stressed area of the part, or maybe you need to MIG weld a plug in that exit hole, but there's various ways to address that. And there's also more complicated friction stir welding processes that are done that eliminate exit holes, but you get the idea. In the summer of 1975, I was working as a construction inspector and surveyor in south central Missouri, and I'll tell you, it really got hot down there. And at the end of the day, it was really nice to come home to a cold beer. Now you're asking yourself, what does this have to do with aluminum welding? But I'll get there. And I'll say that the summer of 1975 is also the first year that light beer was introduced. And Miller went on a campaign, ad campaign, and they said less is more. And that was their promotion for light beer. Less calories, you get it. So. And I saw that and I said, wait a minute, less is never more, more is more. That doesn't make any sense. But being very thirsty and willing to try different beers, as I always am, I said, yeah, let's give them a try. I tasted Miller Lite, and I came away from the process convinced that no, less is not more, more is more. Light beer is a travesty. It's the worst thing that ever happened to beer. How could you take something as good as beer and ruin it by trying to make light beer? So I became convinced that no, less was never more. Until a couple of years later, I got involved in aluminum welding, and then I realized, there are times when less is more, and that is in welding aluminum. The less welding you do on aluminum, the more better off you are. And that's for many reasons. First of all, no matter how perfect your welding process is and how good your welder is, welding decreases the base metal strength of virtually all aluminum alloys that have been tempered to get a little more strength. So it wipes that out. Not only that, welding can distort members because you get differential cooling. You have residual stresses that result in distortions, and that can be a real problem. Not only that, the strength is proportionate to the size, but the cost is proportionate to the size squared in any weld, and that applies to steel welds as well as aluminum welds. And so as you increase the size, the cost goes up a lot faster than the strength, and that's a problem. So you want to keep your welds small. And that's a problem for people who are traditionally welding steel because they figure, hey, if I give you a larger weld than you call for, you ought to be happier than a pig in slop, and that's just wrong. In the case of aluminum, less is more and more is less. Okay, well, let me give you some sources of information because I'm not going to be able to cover everything for you here, but I do want to mention three good sources. One is the American Welding Society, not only because they carry the Structural Welding Code D12, but other publications such as the Practical Reference Guide to Welding Aluminum. The American Society of Mechanical Engineers Boiler and Pressure Vessel Code, and the Aluminum Association, which we'll talk a little bit more in depth. The Boiler and Pressure Vessel Code, Section 9, has got a lot of good information on welding aluminum vessels and vessels of other metals. And so if you're involved in vessel and boiler type applications, that's something to look at. But the Aluminum Association goes back to about 1933, and today it consists of over 100 members that are all the major U.S. aluminum producers and suppliers, and it writes most of the standards that are used worldwide on aluminum, which is a very good thing for Americans because we're more familiar with these standards and these ways of designating aluminum alloys and so forth. And so this can be a very nice thing for us. I provide their contact information there, but suffice it to say that aluminum.org will get you to their location. They're in the Washington, D.C. area, but their website contains all their publications and a nice bookstore to get them. And by the way, if you think I'm promoting any of these organizations or their books, hey, I don't get any commission off their sales, so I don't mind if you buy them or not, but I'm just trying to point out what might be useful to you. And one of the best books ever written about aluminum welding is an Aluminum Association publication called Welding Aluminum Theory and Practice. Now, it's become a little bit dated since the last edition was 2002. We've been working for the last year or so trying to rewrite it, and it's almost ready to be republished. So you might want to think about holding off before you buy the next edition, but it's a very good and very informative look at aluminum welding. But the 2020 Aluminum Design Manual published by the Aluminum Association is probably an indispensable book when it comes to designing aluminum welds, because it has all the rules for determining the allowable strength of an aluminum weld of whatever type. And the 2020 Aluminum Design Manual obviously just came out in the last year, so it's rather current. It's issued every 5 years, so you probably won't see another edition until 2025 or possibly even 2026. They may be going to a 6-year cycle. So my wife would use a different term for it, but I'm very cost conscious. Let's use that euphemism. And so even I would buy this book, given that it's going to be another 5 years before I'll need another one. And it's well worth it because it gives, as I say, all the information for design. Now, there were previous editions going all the way back to 1994. Those were all useful in their time. But the one thing that was most important about the Aluminum Design Manual, and still is that part 1 of the manual is the heart of the manual, and it is the specification for aluminum structures. So if I've lulled you off to sleep at all during this talk so far, I just want you to perk your ears up here and know that the specification for aluminum structures, which I'll abbreviate by its acronym SAS, is where you go to get design rules for determining the strength of aluminum connections, including aluminum welds and including aluminum members. So I highlighted for you here, listing the table of contents, but I do want to also mention that the Aluminum Design Manual has got some other very useful parts. For example, part 6, Design Aids, contains lots of handy design charts, including welded allowable aluminum stresses, and part 7, the illustrative examples, includes welded connections that you might find useful, particularly for those topics. But the Bible of aluminum welding is the AWS D1.2 code. And you know, you could say there are only 3 things you need to know about aluminum welding. The first one is D1.2, the second one is D1.2, and lastly, you get it, D1.2. And I say that, you know, obviously it's the old joke like in real estate, but it's very true. And there's no substitute for having D1.2 and having a basic understanding of it if you're going to do aluminum welding in the United States. Now, this document is supposed to be revised, reaffirmed, or withdrawn every 5 years, but the last edition was 2014, and here it is 2021, and we're still struggling to get another edition out. I think the next edition will very likely come out before the end of the year. The pandemic had nothing to do with the delay in this publication. Rather, it was internal issues at AWS and in satisfying the various committees that need to approve this code. But at any rate, this is coming out soon as a revision without terribly many changes, but a few important changes from 2014. And I give you the contact info there at AWS in case you want to get a copy. Now, D1.2 scope is welded aluminum structures, and that includes anything that you call a welded aluminum structure, and that's just sort of a general moniker. There are other codes. I mentioned the boiler and pressure vessel code that address particular applications like pressure vessels. And there are yet federal codes that involve tanker trucks that go down the highway. But D1.2 is for everything that doesn't fall in a particular application with another code governing. It covers all thicknesses of aluminum parts. So you can weld together sheet metal, you can weld together 8-inch thick parts. but it does not include all aluminum alloys, rather only those that it lists in a table 4.1. And so it typically does not include aerospace alloys like the 2000 and 7000 series because of their copper content, they're not easily arc welded. They can be friction stir welded. That's another reason to be aware of friction stir welding. But those are the only limitations in D1.2. Now, the table of contents for D1.2 I list for you here, and I really want to call your attention to the highlighted topics here: design, qualification, fabrication, and inspection. Now, we only have time today to really talk about design, so we're really only going to talk about 1/4 of the topics, but this is the order in which the whole process needs to be performed when you're doing aluminum weldments. First, you design them, then you qualify a procedure to make the weld and for a welder to perform that procedure. Then you fabricate the weld, and then you inspect the finished product. And there's a lot to those other steps, and I'll talk about some ways you can get up to speed in those if you're interested at the end. Now, a lot of people are familiar, if they're familiar at all, with AWS structural welding codes with D1.1 because D11 came before D12, and it's the steel welding code. And a lot of people that are familiar with D11 want to know, well, what's different about D12, just for a point of reference. And I think that's a handy way to look at things here. And there are some fundamental differences. One, there are no pre-qualified weld procedure specifications in D12. You have to qualify every procedure that you use. And that's a big difference. There are very few, if virtually no, design rules in D12. The nice thing about D12, in my mind, in my view, is that it refers you to the specification for aluminum structures for those design rules. So there's no competing design rule sets in different documents. D12 tells you for design, go to the specification for aluminum structures. The other thing is that there are no thickness limits in D12, unlike D11, which only goes down to a minimum thickness of, I think, something like 3/16. Now, D12 also divides aluminum structures into one of 4 categories. And this little matrix here shows you what the determining factors are. But essentially, it comes down to, is the structure statically loaded or cyclically loaded? And by cyclically loaded, you can think of those structures that are subject to fatigue, for example, bridges. And then the other issue is the structure a tubular structure or a non-tubular structure? Now, when it comes to what's the most demanding and least demanding, it comes down to statically loaded is easier than cyclic loaded, and non-tubular is easier than tubular, for a reason we'll see in a second here. And so statically loaded non-tubulars, those are the types of structures that are easiest to weld. Cyclically loaded tubular structures are the most difficult. Now, it might be obvious that static loads are a little easier and less likely to crack your weld than cyclically loaded situations, but what's up with the tubular stuff? I mean, how does the weld know whether you're welding a tube or a plate? Well, this picture was not originally intended to illustrate the difference, but I think as soon as I saw it, I realized that it does a great job of doing that. And the reason that tubular welding is more difficult is it's very difficult to see the backside of a weld on a tubular part. To inspect the weld back there, or to put a backer bar back there, or to back gouge back there and weld from the other side is almost impossible because you don't have the access. And so tubular welding is much more difficult than non-tubular. And in extrusions, we tend to think of hollows as opposed to solid shapes, but you get the idea. Okay, enough of a general introduction. Let me now talk a little bit about the metallurgy involved here. And we'll talk about the metallurgy of the base metal, that is the parts to be joined, the metallurgy of the filler metal, that is the metal that we're going to fill the joint with and make the connecting material. And then when those two parts get melted together in some sort of a mishmash or mixture, that's referred to as the weld metal. And its composition is going to be somewhere in between the base metal and the filler metal, depending upon how much dilution of the base metal or the filler metal occurs in the joint. And that's going to be a function of a lot of factors, and yet that's going to determine the strength of the joint. Now, I mentioned earlier that when you weld aluminum, you typically reduce any strength that you got from tempering. And the tempering processes like strain hardening or artificial aging are used specifically to strengthen the aluminum from its base metal condition. And when you weld it, you wipe those out. So that's a big drawback in welding aluminum. And any kind of heating, for that matter, a fire, a paint bake cycle, can have that effect unless it's very controlled. And in the case of welding, the temperature is so high, it's above the melting point, that it's going to reduce the strength on either side of the joint, and that's inescapable. So for H-temper material, welding reduces the strength to the annealed condition. And for T-tempers, it reduces the strength to something a little bit less than the solution heat treated, or T4 condition. And then keep in mind that some alloys are not arc weldable. Those would be typically in the 2000 and 7000 series. So to kind of show this graphically, to maybe a little bit clearer, there's the non-heat treatables and the heat treatables, and they respond a little bit differently. But most extrusions tend to be heat treatables, say 6063, T5, T6. And what we see there is that if we've done a precipitation heat treatment in addition to a solution heat treatment, so we have a T5 or a T6 temper, for example, when we weld it, we're going to reduce the strength to something less than the T4 strength, but something a little bit more than the annealed strength. So what is that strength? How do we know what that number is? Well, fortunately for us, the welded strengths of the base metals are listed in the specification for aluminum structures in table A43. And the notation there is to add a W to the subscript. So for when you see F sub TUW, that means the tensile ultimate strength in the welded condition. And the TYW would be the yield strength in the welded condition. Now, very fortunately for everybody, the AWS D1.2 table that gives the tensile ultimate welded strengths for the base metals has got the exact same numbers as the specification for aluminum structures. And the requirement that D1.2 has is that if you're qualifying a groove weld procedure, you must attain in your testing the tensile ultimate strength in the welded condition that's given in these tables. And that is determined by a tension test of a reduced section specimen, or sometimes referred to as a dog bone specimen for obvious reasons from its shape. And so that's a tension test that's used to determine the strength of groove welds to prove that your weld is not going to be the weak link for a groove weld, and that you're going to develop the full tensile ultimate strength in the welded condition of the base metal. Well, so what does that do to the strength of the base metal? Well, I've got 4 examples here. 2 of them are plates, 5052 and 5083, not extrusions. And the other 2 are 6000 series extrudable parts, like 6061 or 6063. And just to give an example here, for 6061, if I have it in the T6 condition before welding, and it's an extrusion with a 38 KSI minimum tensile ultimate, I go and I weld it. Well, I drop the strength down to 24 KSI. So take a big whack. And that reduction in strength is not something that I can overlook. I've got to factor that into the design. And not only that, the yield strength goes down even more. It goes from 35 KSI down to 15 KSI, less than half. And again, that can't be overlooked. It must be accounted for in the design. Now, that's the base metal. For the filler metals, their welded strengths are given only in the specification for aluminum structures in table A46. They give the tensile ultimate strength there, and they say that the shear ultimate strength is just 60% of the tensile ultimate strength. D1.2 is totally silent on filler metal strengths, and so you've got to get them from the specification for aluminum structures, and I summarized those strengths here in this chart. And you can see here, I've highlighted 4043 and 5356. And the reason I've highlighted those is they are the most common fillers that are used. And they're both suitable for being used with 6000 series extrusion alloys. And so they'd be ones you'd be interested in. And you'll see that 4043 has a strength of 24 KSI, which just matches 6061's strength. And 5356 is considerably stronger at 35 KSI. Now, A510 is a publication put out by AWS, and it addresses filler wires and rods. And the current edition of 2017 does not have any specified strengths either. And so again, the only place you can get the strength of filler metal is to go to the specification for aluminum structures in the aluminum design manual. A510 though does have other requirements like chemical composition and important things like packaging and labeling, which you might be surprised at how important that is in preserving the usability and the quality of filler wires. But A510 is useful in at least those regards. Now, because there's a bunch of different filler alloys, and even if you're only going to confine yourself to 4043 or 5356, there are oftentimes questions that people encounter. How do I pick what filler alloy I'm supposed to use? And to be honest, there are quite a few factors that need to be taken into account, or that may be taken into account in picking the filler. But I would say the first two are the fundamental and most important. First of all, the strength has to be chosen properly. If you're doing a groove weld, the strength of the filler metal has to equal or exceed the strength of the base metal in the welded condition. Otherwise, you're not going to be able to pass that qualification test with that little dog bone specimen, and you can go no farther. The other thing is that the chemical composition of the filler metal and base metal have to be compatible so that you don't get hot cracking. Certain compositions of certain trace or alloying elements can be very prone to hot cracking. In other words, as the weld is cooling from its molten condition, they're very sensitive to cracking, and those combinations just those dogs won't hunt, so they don't work. But there are other considerations like ductility, corrosion resistance, what surface temperature you're going to be at, what sort of a color match you're going to get, particularly if you do a clear anodized. And the appearance, how the bead looks, whether you get a smooth bead or a ripple bead, whether you're post-weld heat treatable or not, depending upon your selection. And so those can be important factors in various more refined considerations. Now, if you want to just follow the rules and avoid hot cracking, you can just select a filler alloy using tables that are given either in the specification for aluminum structures or in D1.2 or in A510, the AWS publications. And it can seem really complicated because there are 40 different filler alloys listed in A510, for example. But 9 times out of 10, well, or 85% of the time, I'll say, it comes down to 4043 or 5356. And just to compare those two for a moment, 4043 is a little more fluid, a little less viscous, and it doesn't suffer so much from the black smut that's produced by the high magnesium content of the 5356 filler. But 4043 is less ductile and has lower strength than 5356. On the other hand, it has less cracking sensitivity and better penetration. So there's not a clear winner when it comes to deciding between these two, but rather it depends on your needs and your particular type of weld. Now, I mentioned crack sensitivity, and if you want to put a little finer point on it, the composition of the weld metal after the weld is made, mixing the base metal and the filler metal, will dictate whether or not you're in the crack sensitive zone based on a certain composition of the alloying element. So for example, if you've got silicone in your base metal and filler metal, you want to avoid silicon content in the weld metal of between 0.5% and 2%. That's where the crack sensitivity is the worst. And so if you can anticipate what the dilution will be in your joint, then you can anticipate whether or not you'll be in that crack sensitive composition. Just to illustrate it, you have very little filler dilution in a fillet weld, as you can see on the top of this figure, and very high dilution of the filler metal at the bottom here, which is a square groove weld. And a V groove in between is going to have a dilution of the filler metal somewhere in between a fillet weld and a square groove weld. And so these are things that are important to keep in mind, and therefore what filler metal might work for a fillet weld might not work very well at all for a square groove weld in terms of cracking sensitivity. And the way the composition of the weld metal is calculated is simply based on how much dilution you have and what the composition of, say, the magnesium is in the base metal and the filler metal, as I show in this example here. A square groove weld or a V groove made in a base metal 6061 with filler metal 5356. Well, now that we've talked a little bit about the composition of the base metal and the weld metal and filler metals that are used, let's talk a little bit about design. That'll be our last topic. D1.2 says design welds in accordance with the specification for aluminum structures, and the specification for aluminum structure says produce welds in accordance with D1.2. So these two documents fit hand in glove. It's a nice fit, and they dovetail well. The specification for aluminum structures is divided into a series of chapters with letters as their title. So for example, chapter J, which I've highlighted at the bottom of this slide, design of connections, it deals with design of bolted connections, welded connections, and so forth. And that's a chapter that we would typically want to look at if we're talking about designing aluminum weldments. But there are other chapters that are included in the specification for aluminum structures. Won't talk at length about those here, but suffice it to say that the specification covers all aspects of aluminum structural design, not only strength, but serviceability. In other words, for example, making sure that parts don't deflect or structures don't deflect more than they should in order to maintain their serviceability. Now, there are two aspects to welding design that are covered in the specification: welded connections and welded members. Now, we don't have time to get into the design of welded members, but that's covered by chapters D through G for various types of stress. And just leave it to you to be mindful of the fact that welding not only affects the strength of the connection and it needs to be considered there, but you also need to consider the effect of welding on the strength of the members themselves. And if I see one error more frequently than any other, it's the fact that people overlook, they size the weld and they look at the connection strength, but they don't look at the effect of welding on the strength of the member. So that's something to keep in mind. Now, welded connections, the only material strength that we need to be concerned with is ultimate strength, because we don't worry about a little bit of yielding that goes on in connections. But when it comes to welded members, we need to know the yield strength as well as the ultimate strength. And so it's a little bit more complicated. Now, when it comes to welds, we want to first be aware of what type of joint we have, and then we can talk about what type of weld we have. So the joint types that are typically encountered in structural applications are butt joints, have two parts, two plates, for example, or maybe they're extrusions, end-to-end butted. I have corner joints and I have T-joints. These are the different types of joints, and they're described in various American Welding Society publications, but there are weld types, and different weld types are suitable for different joint types. For example, the groove weld that I'm showing here is in a butt joint. Now, groove welds and fillet welds are the ones we're going to talk about here, again, due to the limits of time, but there are other types of welds like plug and slot welds and stud welds that are also done in aluminum and have their individual niche applications. Well, here's a groove weld, a picture I took in a sign shop up in Milwaukee, and this is a groove weld between two parts that are, I forget, 3/8 or a quarter of an inch thick, typical example of a groove weld. Now, in order to determine the allowable strength of a groove weld, we take the allowable tensile stress times the effective area of the weld. The effective area is going to be the size of the weld times the effective length of the weld. Now, the size is different depending upon whether we have complete joint penetration or partial joint penetration. If we have complete joint penetration, the size of the weld is the full thickness of the part. If we don't have CJP, we have PJP, partial joint penetration, then the size of the weld is going to be equal to the depth of preparation, or in other words, the depth of that groove that you saw in that sample weld above. And the effective length is just the width perpendicular to the direction of stress. Now, how do you know if it's a CJP or if it's a PJP? Well, the basic rules are, with small exceptions, it's CJP if you weld it from both sides. And first you weld it on one side, you flip it over, you back gouge the crud and stalagmites drooping out of the backside by back gouging, and then you weld the backside. Or you weld it from one side with an integral or removable backer on the backside to prevent the crud and the stalagmites from accumulating on the backside. Otherwise, it's PJP. In other words, you welded it from both sides, but you didn't do the back gouging, or you welded it from one side without a backer. Why would you weld it from one side and not have a backer? Maybe because it was a tubular part that you were joining and there was no way to get a backer on the back side. Now, the allowable tensile stress is the other part of the equation once we've got the size of the weld and the area of the weld. And the allowable tensile stress is the least of the base metal welded tensile strengths and the filler metal tensile strength. We get those base metal welded tensile strengths from the specification for aluminum structure table or the D12 table, and we can get the filler metal strengths only from the specification for aluminum structures. And so the strength of a groove weld is really just another demonstration of the principle that a chain is only as strong as its weakest link. So we have base metal in the heat affected zone on one side of the joint, the filler metal in the middle, and the base metal on the heat affected side of the other side of the joint. And let's say, for example, I'm welding together 5083 and 5456 with a 5183 filler. Well, in that particular case, I need to look at the strength of each of those three parts. And for the base metal, let's say that it's a 4 by 3/4 inch thick bar. And let's furthermore say that I'm going to weld it from one side without a backer, and I'm going to use a 5/8 inch deep V groove as my preparation. The reason we make that V groove, by the way, is to allow the welder access to the root of the joint so that he can get the penetration at the root. But if we don't use a backer or we don't back gouge and weld from the other side, we can't be assured of fusion beyond the root, and therefore that last 1/8 of an inch of thickness of the material here doesn't count as the size of our weld. So this weld is a PJP because I didn't use a backer, and the size is 5/8 of an inch, the depth of preparation. The length is 4 inches because it's a 4-inch wide bar, and that makes the effective area 2.5 square inches. Now I need to determine the tensile strength, and for the base metal on the 5456 side, that's 42 KSI. For the 5083, it's 40 KSI, looking those up from the tables. For 5183 filler metal, that's 40 KSI. So the least of those three is 40 KSI. And now I'm going to be able to calculate my strength. One more thing, though, that you need to be aware of, and that is that for PJP welds, once we've calculated the allowable load, we need to factor it by 0.6. In other words, we need to reduce its strength by 40% because of the notch effect of not having fused metal at the base of the joint. Therefore, I apply that 0.6 factor times the area of the weld, 2.5 square inches, times the 40 KSI strength. I divide it by a safety factor, which for building structures is 1.95, given by the specification for aluminum structures. And that gives me an allowable load of just shy of 31,000 pounds, or 31 kips, a kip being 1,000 pounds. That 0.6 factor, as I said, is just accounting for the notch effect of that potentially unfused metal at the root of the joint. And I strongly discourage you from using PJP groove welds for that very reason. You've got that factor that knocks your strength down, and the fact that you've got a built-in crack essentially at the root of your joint doesn't give me great confidence or hope for the future for that type of joint. Now, fillet welds, on the other hand, you calculate their effective area by determining their effective throat, which we'll see a picture of, times their effective length. And just like in steel, we consider that stress on a fillet weld is shear on that area, on that throat, for any direction of load. It's not really true. There's a combination of tension and shear on that throat, but we always consider the stress to just be shear there. And that's a conservative assumption because the shear strength is less than the tensile strength. And the strength then is going to be least of the base metal welded strengths and 85% of the filler metal shear strength. That 85% factor is the knockdown factor for fillet welds. And that's because fillet welds represent a disruption in the stress flow through a part. They represent stress risers both at the beginning and at the end of the weld as you're going down the length of the weld. And then cross-sectionally, they represent an abrupt transition between the weld metal and the base metal. And therefore, that 15% knockdown, in other words, applying a 0.85 factor, is designed to take that into account. And here's a fillet weld on the base of a light pole, for example, and you can see a nice triangular cross-section weld in that view. So you get the strength, the tensile ultimate strength of the filler metal from the specification for aluminum structures. And for the fillet weld, then we're going to take 85% of 60% of the tensile strength, because remember, the shear strength is 60% of the tensile strength, and we consider shear to be acting on fillet weld throats. Therefore, that works out to be 51% of the tensile ultimate strength. For base metal, we don't have that 0.85 factor because it doesn't have the stress riser that the fillet material does, and so it's just 0.6 times the tensile ultimate strength. So here is an example of a T-joint, and we have 6061 as our base metal and 4043 as our filler metal. And in order to design this weld, if they have 4043 filler metal, you would look at three lines of stress. The line that's represented by AC, or the green line, and that would be shear in the base metal. The line represented by the purple line, the AB line, which would be tension in the base metal. And then the red line, the throat of the weld, or the AD line, representing the shear on the throat of the weld. And we would calculate the stress on each one of these, and we could determine which one was the least. And we're typically going to find, and in almost all cases we'll find, that the filler metal allowable is the governing strength of the joint. It's 6.3 KSI, whereas we have stronger strength of the base metal in shear and stronger yet in tension. And of course, we would expect that because tension strength is always greater than the shear strength. And that brings up the question, is the strength governed by the base metal or the filler metal? And in fillet welds, for almost all common applications, the filler metal will govern the strength of the design. The only exceptions are when you use 5000 series fillers to weld 6063 base metal. And you guys might actually encounter that in extrusions. So that's the only time when the base metal will govern. All other times it's going to be the filler metal. And what that means is that you need to make the weld length appropriately long for the base metal. So when you have a case where the filler metal governs the design, you need to size the size of the fillet weld and the length of the weld in order to match what your demand on that particular joint is. This is very much unlike groove welds, where the base metal strength governs the weld strength. So in groove welds, it's the opposite. You choose the filler metal so that it matches the base metal strength, the weaker of the two at the very least. And that's necessary in order to pass the qualification test for the procedure to make the weld. Well, I thank you very much for listening today. If you want more information about aluminum welding, you could go to the American Society of Civil Engineers. There's a seminar there given on aluminum structural design, which covers not only the design of weldments, but also the design of welded members. And the American Welding Society offers a 6-hour course, which is a lot, incorporates what I've said here today and a lot more. I co-sponsor that with a real live in-person aluminum welder. We have a lot of fun with that. The next one's coming up here in July. And if you're interested in those, you can check them out with AWS or ASCE. But thanks for your attention. And now I'll turn it back over to Nancy, and we'll talk about any questions that come up.
Thanks, Randy. That was a great presentation. And if you can stick around, we will be answering a few questions. We'll go over maybe a little bit over an hour here, but we do want to try and get some questions answered. As a reminder, if you have a question, select question or chat from the toolbar and type your question in the dialog box, and we'll try to get to as many questions as we can today. So we do have a couple of questions. Let me start with Mark, who asks, per AWS, what should we ask welders to provide to perform welding?
Very good question. When I'm the structural engineer of record or the engineer in general for a particular welded structure or welded connection, I require, and this is what D1.2 requires, I require that two things be submitted to me before any production welding begins. That is the Qualified Weld Procedure Specification, or WPS, and the record that's used to document it, which is referred to as a PQR, or a Procedure Qualification Record, and the similar documentation for the welder, and that's usually referred to as a Weld Performance Qualification Record, and I require that those be provided to me before production welding begins. it's a whole lot easier to prevent errors or flaws or whatever you want to call them, indications, bad things from happening than producing them, having to find them, and then having to fix them. And sometimes the cure is worse than the disease. So requiring that those records be provided before production welding begins is an excellent idea. And I usually require that contractually or by agreement before any other things are done.
Okay, thanks. And this next question comes from our friend Craig. There are other types of welds for aluminum. Tubing is often welded onto the end pieces or other parts by using inertial welding, where the tube is spun and then pressed to the mating part. There is a similar method with reciprocating linear motion, where aluminum plate can be welded onto another plate or part once pressed together. These methods seem similar, but don't use a separate pin or rotating tool. Where can we find more information about these types of aluminum welds?
Good question. Those are friction welding applications, not friction stir welding, but friction welding applications. And so, as Craig noted in his question, they're like friction stir welding, but they don't use a stir. They just use friction between two parts. You can find more information about those from AWS. They provide other documents related to those specific applications, or in that Welding Aluminum Theory and Practice. I would note that those are, niche applications. They depend on some rather specific situations, maybe a tube to plate connection or something like that, where you can rotate a part or you can move a part in a particular manner, and the joint is suitable for that. But those are other good ways. And some of those basically take the welder skill out of the equation because they're done by robots or by machines. And so really, once you set the machine up, they just always do the same thing over and over again. And in that sense, can be very reliable, assuming that the process is appropriate. In other words, the rotation speed or the number of turns or whatever is what's needed to make the joint properly.
Okay, thanks. Next question comes from John, who asks, where did the 60% factor in fillet welds come from?
Well, the 0.6 factor in fillet welds is just a sort of a material. It's called the von Mises criteria, and it's used in steel as well as aluminum. So it's not an aluminum specific factor. But generally speaking, the shear strength of a given material is approximately 60% of the tensile strength of a material. To be more specific, it's the tensile strength divided by the square root of 3, I believe, which comes out to something like 58% or something, but it's typically rounded to 60%. But that's just the relationship in metals in general between the shear strength and the tensile strength. And remembering that when we do fillet welds, we're only concerned with the shear strength. And so we need to get that shear strength from the tensile strength by applying the 0.6 factor. I hope that addresses that.
Okay. This next question comes from Jonathan, who asks, where can we find effective throat of flare bevels? Is it the same as steel?
Very good question. We've had some serious debates and discussions about that at AWS committee meetings. There are those who maintain it should be the same as steel, others who maintain no. And when we tried to get the rules changed to get the throat of a flare bevel groove weld made the same as steel, we got voted down. I don't know that there's really that much of a difference, but there have been new proposed rules, because you won't find that in AWSD 1.2, as I imagine John has come to realize if he's looked in there. But there are proposed rules. They won't make the 2021 D1.2 issue, and I don't know when the next issue will be, but it could be as long as 7 years from now. So that's not very helpful for this person asking. If John, if you send me an email, I will dig up what the proposed rules are for the AWSD 1.2. Not to say that they will appear anytime soon, but I can give you what's proposed. It's typically a fraction of, it's done just like steel, a fraction of the radius of the part being joined.
Okay. Let's see, the next one. I have a couple of questions. One of the questions came from somebody who's left the webinar already, and a related question from somebody who's still with us. So maybe the gentleman who left will listen in on the recording. First, they ask, can anodized aluminum be welded, and what are the considerations? And from Michael, he asked, does anodic surface have to be ground off before welding anodized extrusions?
The simple answer is you need to remove the anodized surface before welding. There are some very fancy trick ways to weld through anodizing, but I don't recommend it. It's for not for the faint of heart. So generally speaking, the only way to practically do it is to remove the anodizing or to anodize the structure after it's welded, which is probably more often done. If you anodize before welding, the weld is going to stick out like a sore thumb from an appearance standpoint because it won't be anodized typically, and that's kind of ugly. And you have the issue of removing the anodizing, which is a heavy oxide surface, and you can't weld through oxide, which also illustrates you can't weld through water staining. If you've ever seen the white water stains or gray or whatever, that's oxide, and you don't want to try to weld through that because you're going to have similar problems as trying to weld through anodizing.
Okay, I'm going to ask one more question because I want to be mindful of everybody's time here. But one last question, how to design the minimum penetration for a flare groove weld?
Well, I'm not sure I understand the question entirely. It may be related to I think it was John's question about what's the size of a flare bevel groove weld. Again, I don't know what's proposed. I don't recall it in the back, but I can look that up if I get an emailed question, and that might address that more precisely for those folks.
Okay, great. So yeah, if anybody has a question that we haven't addressed here, feel free to contact Randy. His contact information is on that slide there. So,
Right.
So thank you again, Randy, for a great presentation. Today's webinar will be available online soon at the AEC website, and we will send you a link once it's uploaded. The evaluation survey for this webinar will be sent to you following this presentation, and please share your comments with us. Your input is very valuable and helps us in developing future webinars. Be sure to visit our website at aec.org/webinars for more upcoming webinars on aluminum extrusions and links to previous webinars available on demand. The website also has information and resources for aluminum extrusion design, applications, technical information, and much more. This concludes today's presentation, and have a great rest of your day. Thank you, everybody.